Hello students, today we are going to see Fermat's theorem. Fermat's theorem basically deals with finding the remainder when a very big number is divided by a prime number. So this is one of the applications of prime numbers. This is one of the applications of congruence relations. So this is a statement of Fermat's theorem. A is any integer and P is a prime such that P does not divide A. So A is not divisible by P. Then A raised to P minus 1 is congruent to 1 mod P. That means the P minus 1 power of A, when it is divided by P, the remainder is 1. See, when P is divisible by A, any power of A would be divisible by P. Sorry, when A is divisible by P, then any power of A would be divisible by P. So there is no need to apply any theorem. Here, that's why we are assuming, we are considering the condition that P does not divide A. In that case, A raised to P minus 1 is congruent to 1 mod P. And using this particular formula, we can find out remainder of any power of A when any power of A is divided by P. So here I have taken one example. If I want to see 11 raised to 405, it is going to be a very big number, which the number cannot be displayed on the calci also. It will show you something into 10 raised to some powers, okay? So we don't know how many digits are there right now also in that number. So basically it's a very big number, and that is to be divided by 13. So let us see how we can apply Fermat's theorem. 11 raised to 405 is divided by 13. So here I am considering A as 11. So definitely it is an integer. Then P, the number by which you are dividing. So that is 13, and 13 is a prime number. And 13 does not divide 11. And therefore, we can apply Fermat's theorem here. Therefore, by Fermat's theorem, I can say 11 raised to 13 minus 1 is congruent to 1 mod 13. So, when 11 raised to 12 is divided by 13, the remainder will be same as, remainder is equal to 1. We want to reach to 405. So, we are getting some number, 11 raised to some number. So, if we assume that this is your n, 405. So, we will divide n by p minus 1, which is nothing but 12 here. Okay, so p minus 1 is equal to 12. Now, here, one more thing is to be observed, that if your n, the power given in the problem, is divisible by p minus 1 itself, then the remainder is going to be 1. That means if I take 11 raised to, say, 360, then I can write 11 raised to 360 as 11 raised to 12 raised to 30. So it is going to give me the same remainder, 1 raised to 30 mod 13, using the properties of congruence relation. So if this power is divisible by p minus 1, then answer is going to be 1. We don't have to do many calculations here in that case. But right now we are given 405. So you observe that 405 is not divisible by 12. So 405, when I divide it by 12, I get remainder as 9. So 11 raised to 45, 405, I can write as 11 raised to 396, right? 360, and so 12 into 333, it will give you 396, 360 plus 36. Okay, so 11 raised to 396 into 11 raised to 9. So for 11 raised to 396, we need not to worry. Though it is a big number, it is a multiple of this 12. So it's going to give me the same remainder as that of 11 raised to 12. So 11 raised to 396, I can write as 11 raised to 12 raised to 33. And this is congruent to what? 1 raised to 33 mod 13. As 11 raised to 12 is congruent to 1 mod 13. So I can simply make 33 copies of this. 11 raised to 12 into 11 raised to 12 into 11 raised to 12, 33 times is congruent to 1 into 1 into 1 into 1, 33 times. So that is ultimately going to give me 1, remainder as 1. So here I have to worry about these 9 copies of 11 now. I have to check what happens when I divide 11 raised to 9 by 13. So let us see. So we have got this equation right now. 11 raised to 396 is congruent to 1 mod 13. So I'm putting this as equation number 1. Now I want to talk about 11 raised to 9. When I divide 11 raised to 9 by 13, what is the remainder? So I can mathematically, I just can say 11 raised to 19 mod 13 is equal to how much that I want to find. So let us start with 11 itself. So 11 is less than 13. So when you divide 11 by 13, the remainder is going to be 11 itself. Let us do 11 raised to 12, that is 121. If I divide 121 by 13, then 13 6 are 78, 13 8s are 104, 13 9s are 117. Okay, so the remainder is 4. Right? Now I want to go to 9. I want to reach to 9 from 11 raised to 2. So here 9 is a multiple of 3. I have got 11 is congruent to 11 mod 13. And 11 raised to 2 is congruent to 4 mod 13. So using congruence properties, if I multiply these two, then I will get 11 into 11 raised to 2. It's congruent to 11 into 4 mod 13, which is same as 44 mod 13. So when you divide any number by 13, you cannot accept 44 as the remainder. So using transitivity of the congruence relation, now 44 is congruent to 5 mod 13. When you divide 44 by 13, remainder is 5. 13 3s are 39. So this is congruent to 5 mod 13. That means I am getting 11 raised to 3 as is congruent to 5 mod 13. And I want to make 9 copies of it. So I can just simply do that 11 raised to 3 into 11 raised to 3 into 11 raised to 3 is congruent to 5 into 5 into 5 mod 13. Now, so this will become congruent to 125 mod 13, and I can easily divide 125 by 13. So this is giving me, let us see what does it give. So 11 raised to 9 is congruent to 125 mod 13. Now what is 125 mod 13? 125 is congruent to 13 9s are 117 we saw, and 13 10s are 130. So it is going to give me 125 minus 117, that is 8. 8 is the remainder. Okay, 117. 125 minus 117 gives me remainder equal to 8. So this is congruent to, so by transitivity, A is congruent to B mod N and B is congruent to C mod N. So this is A, this is B, this is B, this is C. So A is congruent to B mod N and B is congruent to C mod N. Implies A is congruent to C mod N. This is transitivity relation. Okay, congruence relation is an equivalence relation basically. It is reflexive, symmetric, and transitive also. So this is the transitive property. So I'm getting 11 raised to 9 is congruent to 8 mod 13. Okay, you can see the congruence easily here. I'm writing particularly 11 raised to 19 is congruent to 125 mod 13 and 125 is congruent to 8 mod 13. I am actually dividing 125 by 13. So remainder is 8. So this is my A, this is my B, this is my B, this is my C. And this gives me 11 raised to 9 is congruent to 8 mod 13. So this is my second equation. My first equation was this. Sorry. This was my first equation, right? 11 raised to 396 is congruent to 1 mod 13. And 11 raised to 396 is congruent to 1 mod 13. So if I multiply these two, I can get 11 raised to 405, which I want. So 11 raised to 405 gives me 8 as the remainder. Therefore, when 11 raised to 405 is divided by 13, the remainder is equal to 8. This is how we can apply Fermat's theorem to find out the remainder. As I'm talking about congruence relation, let us see how a congruence relation is an equivalence relation. Okay. Congruence relation is an equivalence relation. So a relation, let us recall what is an equivalence relation. First of all, a relation R defined on a set A is called an equivalence relation if it is, first condition, reflexive. That is, A is related to A for all A belong to capital A. Second thing is symmetric. The relation is symmetric. That is, if for A, B in A is related to B, that implies B is related to A. For all AB belong to A. Okay, this is for all. I should have written for all here itself. And the third condition is, if it is means R, transitive. So when the relation is transitive, the relation is transitive. If A is related to B and B is related to C, then it implies A is related to C for all A, B, C belong to R. So when a relation is reflexive, symmetric, and transitive, then it is called as an equivalence relation. So let us prove that congruence relation is an equivalence relation. Okay. Let me just. So the first step, now I'm going to prove is, let us first define define congruence relation. A is congruent to B mod N. If and only N divides B minus A. Okay. So when you divide A by N, remainder is N, or you can say N divides B minus A means B, when you divide B minus A by N, remainder is 0. So we are going to make use of this particular definition. Okay. So let us prove that congruence relation is reflexive relation. Now, as we know that every integer N divides 0, right? So N divides 0, which I can rewrite as N divides A minus A. And this implies A is congruent to A mod N. So this proves that congruence relation is reflexive. I'm just putting the symbol here. Congruence relation is reflexive. Then second I am going to prove that congruence relation is symmetric. I'm just using this symbol for congruence for time being. Okay, this is not the notation actually. We of course use this notation, but in this fashion we use it. Okay. So congruence relation is symmetric. So let A be related to B. So that implies N divides A minus B, which implies N divides minus of B minus A, right? I'm just rearranging the terms. And as N divides minus of B minus A, N must divide B minus A also. And this says that B is congruent to A mod N according to the definition. Okay, when A is related to B, that implies A is congruent to B mod N, which implies this. And when I get this, B minus A, the order is changed. So B comes on the LHS and A goes on the RHS. But this is possible because of the divisibility property. So your equivalence relation is symmetric also. A third property is transitivity. So let A be related to B, A be related to C. So these two imply that A is congruent to B mod N, and sorry, here I should take B related to C, and B is congruent to C mod N. So what does this imply? A is congruent to B mod N means N divides A minus B. This implies N divides B minus C, right? So I can write A minus B is equal to N times some K1, and B minus C I can write as N times K2. So here K1 belongs to Z, of course, K2 belongs to Z, as we are talking about divisibility in integers. Okay, so now let us add these two equations. Adding, we get A minus B plus B minus C is equal to NK1 plus NK2. So it simply reduces to A minus C is equal to N into K1 plus K2, which is N times some K. A minus C, so K is equal to K1 plus K2. As K1, K2 are integers, K1 plus K2 must be an integer. So A minus C is N times something. So N divides A minus C, and that implies A is congruent to C mod N. So we started with the assumption that A is congruent to B mod N and B is congruent to C mod N. And this has given us A is congruent to C mod N. And therefore, congruence relation is transitive. So as it is reflexive, symmetric, and transitive, congruence relation is an equivalence relation also. So please recall all the properties of equivalence relation, and in general also you should be able to give the examples. If we have some examples in front of us, say example of a relation which is reflexive and transitive but not symmetric, which is reflexive and symmetric but not transitive, we must be able to define those functions, or there are certain standard functions which we must be able to classify whether the relation is reflexive, symmetric, or transitive, or some two properties are satisfied or nothing is satisfied, etc., etc. Thank you very much for watching the video.